Hey, what's up, Chem peeps? Let's do a little bit of free response practice for thermochemistry. The neutralization of hydrochloric acid with sodium hydroxide is represented by the balanced equation below. The enthalpy change for the neutralization is positive 84.3 kilojoules per mole reaction. Okay, take a moment, examine that reaction. Interesting. Part A. Would you classify the reaction for the neutralization as endothermic or exothermic? Justify your prediction. All right, let's take a quick peek at the sign of the enthalpy change. It is positive, so we're going to go with the reaction is endothermic. Boom. Let's think about our justification. The enthalpy change of the reaction is positive. A positive delta H indicates more energy was absorbed to break reactant bonds than was released to form product bonds. Boom. Okay, let's recall what's going on with any reaction. In any reaction, you have to put energy in to break reactant bonds. And in any reaction, when you form product bonds, energy is released. If a reaction is endothermic overall, more energy has gone in to break than was released upon the formation of the new bonds, making the delta H for the reaction overall positive. Remember, energy in is going to have that positive sign. Subpart I. Using your classification, rewrite the above equation as a thermochemical equation. Okay, so a thermochemical equation is going to have the heat term included into the equation itself. And as you think about this reaction, we've already identified that it is endothermic, which means that the heat term is going to go on the reactant side. It's absorbed in order for the reaction to take place. So I'm just going to rewrite my equation as I have it above, and then I'm going to include the heat term over on the product side, which is 84.3 kilojoules. Boom. Thermochemical equation. Part B. Show a numerical setup and calculate the amount of heat absorbed or released by the reaction of 0.40 grams of sodium hydroxide, according to the equation above. Okay, so as you think about this, we're going to use some stoichiometry. Looking at the equation as written, 1 mole of sodium hydroxide requires 84.3 kilojoules of heat. The question is, are we reacting 1 mole or are we reacting more than or less than 1 mole of sodium hydroxide? So the first thing we're going to do is take our mass in grams of sodium hydroxide and convert it to moles to compare what's going on in the balanced chemical equation. And the molar mass of sodium hydroxide is conveniently 40 grams per mole. And then looking at the balanced chemical equation, for every 1 mole of sodium hydroxide, 84.3 kilojoules of heat is required. So if I head to my calculator, I'm going to multiply 0.4 by 1, divide by 40, and then multiply by 84.3 and divide by 1, which will give me 0.84 kilojoules, and because it's positive, absorbed. So think about this. We have 100th of a mole. So we're only going to need 100th of the amount of heat to be absorbed to react that 0.4 grams. Part I. Using your answer to Part B above, show a numerical setup and calculate the expected temperature change in the calorimeter when 0.40 grams of sodium hydroxide completely reacts in a 50 ml sample of HCl. Assume the specific heat of the solution is 4.18 joules per gram degree Celsius, and the total mass of the reaction mixture in the calorimeter is 40.40 grams. Okay, now the first thing we need to think about in this part of the free response is to recognize the law of conservation of energy, that the heat that's absorbed by the reaction is equal to the heat that's released by the surroundings, right? And so our surroundings is essentially, you can think of the water in the calorimeter. Okay, now I know that can be a little tricky to think about when you're thinking about a question like this, but imagine that the reaction is happening inside a little box represented by this red square, floating inside the water. And so think of the reaction itself as inside that red box, and the surroundings is everything outside of that, but still inside the calorimeter. And if you notice when you are performing the experiment that the temperature is going down, essentially the surroundings temperature is going down, and therefore it's losing heat or giving heat off, and the reaction itself must be absorbing it. Conversely, if we notice a situation in which our temperature probe was increasing, right, that means the reaction itself must be giving heat off. And so I often have to think about this in both directions to decide which makes sense. But if you think about the temperature probe as being in the surroundings and the reaction itself is kind of in the middle of your calorimeter, although not exactly true, you can kind of hopefully better understand what's going on with the direction of heat. So for this question, we recognize already that the reaction is endothermic, so it's going to be positive. So the heat of the surroundings is going to be negative. The surroundings must be giving heat off to the reaction in order for this reaction to happen. So if I have 0.84 kilojoules of heat that's going to be absorbed, that means that 0.84 kilojoules of heat must have been given off by the surroundings. So same amount, same magnitude, but different sign. Now, I'm going to then calculate what the temperature change would be in my calorimeter if the water was giving off or losing 0.84 kilojoules of heat. And for this, I'm going to use Q equals mc delta T. But importantly, I'm going to use the negative 0.84, or in joules, negative 840 joules. That's the amount of heat that was lost by the surroundings, which is essentially, right, the water outside of the reaction. So it's giving that heat off, so the temperature is going to go down, right? And so I'm expecting a negative delta T. So my mass here, we're told explicitly in the problem, is a total mass of 50.40 grams. My specific heat capacity, we're told to assume the same specific heat capacity as that of water. And we're solving for delta T. So some quick algebra here. I'm going to take negative 840, divide by 50.40, and then divide that by 4.18. So my delta T is going to be negative 4.0 degrees Celsius, right? That's my delta T. I expect a decrease in the temperature of the surroundings or in the calorimeter. Boom. Okay, so this part of the free response is kind of like what we would expect if we did this lab perfectly, right? So I've got this equation. I know that's an endothermic process. I know that if I reacted 1 mole of sodium hydroxide, I would need 84.3 kilojoules. And therefore, if I'm reacting what is essentially 1/100th of a mole of sodium hydroxide, I would only need what's equivalent to 1/100th of the amount of energy in the balanced chemical equation for 1 mole. And then I can think about how that would relate to the temperature change in the calorimeter. But all of this is done on paper and what we would assume to be like perfect conditions, no error. As you look at the second part, it says a student then performs a calorimetry investigation in order to experimentally determine the delta H of the reaction for the neutralization reaction above. The student measures 0.40 grams of sodium hydroxide, so the amount that we use in the part above, and enough hydrochloric acid, so the total mass of the reaction mixture is 50.40 grams, again, like above. The reactants all originally at 25 degrees Celsius are combined in open polystyrene cup, a coffee cup calorimeter. The temperature is monitored as shown in the graph below. Boom. Take a moment, examine. It says, according to the graph, what is the temperature change in the calorimeter? So remember, temperature change is the final temperature minus the initial temperature. So T final minus T initial. My final temperature is 21.8 degrees Celsius. My initial temperature, 25.0 degrees Celsius. So my delta T, my change in temperature, is going to be experimentally negative 3.2 degrees Celsius. So remember, we expected from a reaction like this to observe a change in temperature to be 4 degrees. And yet, it didn't quite get as cold as we expected. Interesting. Lab error. What? It says, show a numerical setup and calculate the experimental amount of energy in kilojoules absorbed or released by the reaction during the student's investigation. Assume the specific heat of the solution is 4.18 joules per gram degree Celsius. Okay, so we're going to be working a little bit backwards from what we did in the first part of this FRQ. The mass of the solution is still going to be 50.40, right? Just like we did when we did this with the perfect conditions on paper, right? We're still assuming 4.18 joules per gram degree Celsius, but experimentally we determined our temperature change to be negative 3.2. So not quite as big a temperature change as we would have expected. And when I solved this for Q just by multiplying those three things together, my Q, my measured Q, is negative 670 joules. Again, joules because that specific heat is got the unit of joules in there. But remember, we're asked to calculate in kilojoules for the reaction. And again, remember what we're measuring right here in this case is the heat that is essentially released by the surroundings. And so if we're going to calculate the amount of heat absorbed by the reaction in kilojoules, we need to keep in mind that whatever heat is absorbed by the reaction is equal to the heat lost by the surroundings. Again, right now, we've solved for the heat lost by the surroundings, and in kilojoules, it's going to be negative 0.67 kilojoules, or for the reaction, positive 0.67 kilojoules, right? So the heat of the reaction is positive 0.67 kilojoules. That's the amount of heat that we experimentally determined was absorbed upon the reaction of 0.40 grams. And remember, right, we, expected that the reaction would absorb 0.84 kilograms. So, ouch, our experiment right now isn't quite matching up to what we would expect. But let's keep going. Show a numerical setup and calculate the experimental enthalpy change for the reaction. So remember, the reaction is showing us how much heat 1 mole of sodium hydroxide would absorb as it reacted according to this equation. And we did not react 1 mole. We reacted 1/100th of a mole. And experimentally, we absorbed 0.67 kilojoules of heat. So to calculate the enthalpy change of the reaction, we're just going to take our heat of the reaction and divide it by the number of moles that reacted. And in this case, we know, or we calculated, that 0.67 kilojoules of heat were absorbed by the reaction in this lab when we reacted 0.40 or 0.01 moles of sodium hydroxide, which when you divide gets you positive 67 kilojoules per mole of the reaction, right? So what we've done is we've figured out, based on our experimental data, that if I were to react 1 mole, I would only need 67 kilojoules, and that's less than what we were told the delta H of the reaction was at the very beginning. And so the last part of this free response is asking you just to think about, well, is our experimental delta H greater than or less than the accepted delta H? And then provide a valid explanation. So first, let's just answer the question greater than or less than, right? The experimental delta H, positive 67, is less than the accepted value of positive 84.3, which we know from the problem at the very beginning. Classic FRQ requiring to go back and use an earlier part or use earlier information. Boom. So experimental delta H less than the accepted delta H, positive 67 is less than positive 84.3 kilojoules per mole reaction. As you think about what could have caused us to have a lower calculated delta H, think about how this experiment was performed. We did it in a coffee cup calorimeter that was open, there was no lid. And so some of the heat must have been not absorbed by the reaction, but lost to the surroundings. And so when you look at a picture like this and you just assume, oh, the heat's going to go into the reaction as desired, we might forget that, oh, maybe some of it is actually going to come out, which is going to cause temperature change that's not going to be as big as we otherwise would expect. And if the temperature change is not as big as we would expect, right? We expected that to be -4. Then when we do the calculation for the delta H, our amount of heat, our Q, is going to be smaller than what we expected as well. Again, the experiment was performed in an open calorimeter, allowing for some heat loss to the surroundings indicated by a smaller delta T. Smaller experimental Q then resulted, and we ended up with a smaller calculated delta H. So many times with error analysis, you're just going to be thinking back and looking at the calculations you've already done and thinking about how the error that you have could affect those calculations, and then just follow it through again. Okay, you're going to be asked some very similar questions on your FRQ. I hope this helps. Let me know if you have any questions.